So, hello, I'm Volker Weismann. You may know me as the prettiest, the smartest, or the most arrogant guy at this university. And I will talk about the fundamentals and madnesses of quantum mechanics. So first of all, I will compare my field, statistical mechanics, with quantum mechanics. Then I will need to explain some special relativity for those of you that never had the pleasure. Then I will show you the most unclassical experiment ever done. Then I will explain to you how to build a device which cannot be built. And I will explain to you why this does not break special relativity. So in this section I want to show a comparison between classical statistical mechanics and quantum mechanics. To be more exact, I want to show that there's no interference in statistical mechanics, but there is interference in quantum mechanics. And wait, I need to share that off. So you probably all recognize this experiment here, right? Right?
Yes.
Okay, so that's this double slit experiment. On the left, we have a source of classical or quantum particles. Then we have a plate with two slits, and after that, two particles detectors that we can move on a line. I'm a theoretical physicist. I like simple and abstract systems, so we label the cannon, the slits, and the detectors, and consider a simplified, abstracted version of the double slit experiment. I'm going to change some numbers, but the key insights won't change. We first consider the classical case. Our system is initially in a state A1 with a probability of 1. It then transitions to the state B1 or B2, both with a probability of 1/2. The probability of it then being in the state B1 is therefore 1 times 1/2 or 1/2. Same for B2. After that, the system transitions into C1 and C2 with the same probabilities. There are two different paths how the system can up in state C1. Either via this blue path by moving across B1, or by this green path by moving across B2. The probability for the particle moving across the blue path is 1, because that's the probability that we start in A1, times 1/2, because that's the probability that we transition from A1 to B1, times 1/2, because that's the probability that we transition from B1 to C1. This yields 1/4, same for the green part. Now if you have two ways to achieve the same result in classical mechanics, the probability of any of these to happen, the probability of the system ending up in C1, is the sum of them 1/2. Now let's look how this works in quantum mechanics. The core difference between classical mechanics and quantum mechanics is that in classical mechanics, a probability is represented by a number between 0 and 1. But in quantum physics, a probability is represented by an arrow inside a circle with a radius 1. The length of the arrow is the square root of the probability, and the direction of the arrow is called the phase, which is a probability which is a property without a classical counterpart. This arrow is also called the amplitude, or the amplitude of probability. Because we said that the system is initially in the state... Wait a second. Because we said that the system is initially in a state A1 with a probability of 1, this is represented by an arrow with a length of square root of 1, or 1. As before, the system transitions from A1 to B1 or B2 with a probability of 1/2. The length of those arrows is therefore 1 times the root of 1/2, or 1 over the root of 2. Now, unlike in classical physics, the transition can also have an additional phase shift that rotates the arrow. I showed you a phase shift of 0, but the phase shift can also take a different value. Like in the classical case, it then transitions to C1 or C2 with a probability of 1/2. Therefore, like in the classical case, there are two paths how the particle can end up in C1 or C2. The blue path and the green path that we saw earlier. The probability for the particle taking the blue path is represented by this blue arrow here. The length of this arrow is 1, because that's the probability of the particle starting in A1, times the root of 1/2, because 1/2 is the transition probability from A1 to B1, times the root of 1/2, because 1/2 is the transition probability from B1 to C1. Now this yields the square root of 1/4, which makes sense, because in the classical case, the probability for the blue path was 1/4. And we said that the length of the arrow is the root of the probability. So this makes sense. And the square root of 1/4 is also 1/2. The probability of the system taking the green path is represented by this green arrow, which has the same length. So the length of those arrows matches what you would expect from classical physics. But as I said, the transitions can also have an additional phase shift that rotates the arrows, unlike in classical physics. The direction of the blue arrow therefore depends on the phase shift it gets along the blue path, and the direction of the green arrow depends on the phase shift it gets along the green path. Shown here as an example is minus pi½ for the blue path and pi for the green path. The probability of the system ending up in C1 is represented by this red arrow, which we get by appending the blue and green arrow. Now we want to check what happens if we analyze the system for different phase shifts. If the in a double slit experiment, we can change the phase shifts by moving the detectors along the line. If we take this here and add the same phase shifts to both paths, both arrows are rotated by the same angle, which means that the length of the red arrow stays the same. But if we add different phase shifts to both paths, we see that both arrows are rotated by different amounts and the length of the red arrow changes. Because the length of the red arrow is the square root of the probability of the system being in state C1, this means that this probability depends on the phase shifts and not just on transition rates, and not just on transition probabilities, This finding is the most important difference from classical mechanics to quantum mechanics. In quantum mechanics, probabilities don't simply add, they also have this dependency on the phase. As I said before, both arrows have a length of 1/2. Now the maximum value of this probability is 1/2 plus 1/2, or 1, if the arrows are parallel. And the minimum value is 1/2 minus 1/2, or 0, if the arrows are antiparallel. Now, if we would assume uniform distribution for the phase shift difference between the blue path and the green path, the average probability would be 1/2, which was exactly our classical result. That's how the classical result follows from the laws of quantum physics. In classical systems, there are uncertainties in the phase shifts that are big enough that it makes sense to assume a uniform distribution for the phase shift difference. That's why in a double slit experiment you see interference for quantum particles but not for classical particles. The phase shift along the path is the action along this path, which is the time integral of the energy or the Hamiltonian. If we would look at a continuous system instead of a discrete system like this one I showed you, you can use this to show how Hamilton mechanics is just the limit of quantum mechanics. But I don't have the time to show you this here. So, wait a second, we need to share that open. So now, through a completely different path that has nearly nothing to do with what I said before. Before I can explain you that, I need to mention some important facts from special relativity. Shown here is the classical spacetime, and when I mean classical, I mean without the theory of special relativity. Right in the center at t equals 0, x equals 0, there's some main event that we are interested in. The red part is called the future of this event, and it's a set of all events with t greater than 0, or in other words, all events that could be reached if you start at the main event and travel with infinite speed. The blue path is called the path of this event, and it's a set of all events with t smaller than 0, or in other words, all events from which we could reach the main event if we travel with infinite speed. The important thing here is that only events in the past can affect the main event, and only events in the future can be affected by the main event. This rule is called causality. Now things change as soon as we introduce special relativity. We get this figure here, which is called a light cone. In other words, all events that could be reached if we start at the main event and travel with the speed of light. The past is defined similarly. The rule that only events in the past can affect the main events and only events in the future can be affected by the main event still applies. Now if you look at both inequalities here, we can see that there are now events that are neither in the past nor in the future of our main event. This is shown in green and sometimes called elsewhere or raumartig in German. In this case, both events are far from each other in space and happen very close after each other. Neither event can affect the other one. Now if we would search for the origin of this law, we would find that there exist transformations called Lorentz transformations that do not change any measurement but move an event from the upper half of the green part to the lower half of the green part or the other way around. So the transformation changes the order of events but does not change any measurement. That's why both events are separate and we cannot send information faster than the speed of light. That is what I want to show you in this section. Two nearly simultaneously events far apart from each other never affect each other, and sending information faster than the speed of light is absolutely impossible. So let's start with the main part. The most unclassical experiment. So when people are asked what the most crazy, most unintuitive, unexplainable observation in quantum mechanics is, that is the hardest to understand and the most radically different than classical mechanics, they usually point out how measuring a variable can change the system. This is a very important difference from classical mechanics, where, at least within practical limitations, one can measure every variable at any point without modifying the system. But I disagree with it being the most unexplainable unclassical fact. This is because one could argue that there might be an underlying classical reality that we just do not know yet. Maybe it's not the measurement itself that modifies the system, but the way that we measure it. Let's look, for example, at one typical example of the system that changes under measurement: the spin of a silver atom. Usually, we measure the spin by sending the atom through a magnetic field. If you measure the spin along one direction, then measure the spin along another direction, and then along the first direction again, we sometimes get a different value. The typical interpretation is that it is the measurement itself that changes the system. But it is easy to imagine that it's just the magnetic field that changes the system, and there's another way, without magnetic fields, to measure the spin that does not change the system. It is not impossible that beneath the weirdness of the spin of the silver atom, there is a classical system that explains all of it. In other words, we could build a classical machine that acts just like a silver atom or another quantum system. But I will show you in the next section that we cannot build a classical machine that acts just like two entangled quantum systems. Or in other words, how can we build this device that cannot be built? So the big question that we want to answer is whether two prisoners can pretend to be two entangled quantum systems. The rule of the game is as follows. In the beginning, the two prisoners, Alice and Bob, may talk to each other, maybe they flip some coins, and they can try to come up with a plan together. After that, they are separated and no longer able to communicate. Then, each one is asked 0 or 1, which they have to answer with plus or minus 1. We repeat this process many times and define this here as the probability of both answers being equal. QAN, QBN, VAN and VBN are the values in the nth iteration. The divisor here is the number of the times that we ask the QA and QB combination that we are interested in, and the dividend is the number of times we ask the QA and QB combination that we are interested in, and Alice and Bob gave the same answer. In other words, P of QA QB is the probability that if we say a certain QA to Alice and a certain QB to Bob, they will answer the same. So to reiterate and make an example, Alice and Bob come up with a plan, then they are separated. Then we say QA equals 0 here to Alice, and she answers with VA equals +1 here. Then we say QB equals 1 here to Bob, and he answers with VB equals -1 here. Oh, so. The first question to the audience, that means to you, is whether the prisoners can come up with a plan that produces this probability table. We see that if we ask the same question to both, we always get the same answer, but if we ask different questions, we only get the same answer in half the cases. Now, that's my question to the audience. Is it possible for the prisoners to produce this table? Hello?
I would say no,
Why don't you think that this is possible?
because there's a probability of 1. This reason is strong for QA and QB the same.
Is there anyone who has a different opinion?
That it shouldn't be possible. There's no prompt that you can give to Alice they'll get her to give a different result to what Bob will give for the same prompt. Right?
Wait, can you repeat that?
If you give Alice an input of 1,
Yes.
and she answers -1.
Yes.
And if you give Bob a different input, because Bob cannot know what Alice was asked,
Yes.
there's no way what he says can correspond to. There's no way they can have a system that agrees.
Okay. You're wrong. Both of you.
Okay.
There's actually a really simple way that they can do that. When they are together and can come up with a plan, they both flip 2 coins together. And if they ask 1, they answer the result of the first coin flip. And if they ask 2, they answer the result of the second coin flip. That way, they always answer the same if the question is the same, simply because they looked at the same coin flip. And if the questions are different, they look at different coins, and only in half the cases they answer the same. The thing that you seem to forget in our rules, that they are separated, but before they are separated, they can talk to each other and come up with a plan. So they can use this time to flip 2 coins and both remember what the coin flip was. So they have memory of the same experiment. So they can absolutely produce this table. That's actually the reason I wanted to show you this table, because it's a common misconception that this table is impossible, and it's therefore remarkable if a physical system can produce this table. It's nothing special if a physical system can produce this table. Now let's look at this different table shown here. As you can see, they both always answer the same, except when Alice and Bob are both asked 1. In this case, they always answer the same and answer the opposite. Now I ask again the same question as before. Can they come up with a plan that produces this table? Anyone has an idea?
If I would be really honest, then I would say that I didn't understand quite good the previous slide.
Okay.
The concept example.
We can go back. Okay, so so Alice and Bob, so this is the sketch. So Alice and Bob meet and they talk to each other. Yes, and they can come up with a plan. So what they do is, and they want to come up with a plan that produces this probability table.
Yes.
So what they do is, while they are together, they flip 2 coins. And then both of them note down what the result of those coin flips was.
Yes.
Then they are separated. And then we ask Alice 0 and Bob 0. Or Alice 1 and Bob 1. Right?
Yes.
And then, if Alice was asked 0, she looks at the first coin. So that way they always end up with the same. Okay. So good. Okay. So, as I said, the next question is this probability table possible or impossible? Anyone has an idea?
When Alice and Bob, so they flip a coin.
Yes.
The second coin they flip, they say that Alice will always give the answer and Bob will always give the opposite of that coin flip when prompted with 1. The first coin flip, they agree like previously. That's how you get the zero.
So you think
I'm
that
not sure about the
so
tag.
you think that this probability table is possible?
No, I don't know. I can understand how the 0 comes. I can understand how the 1 comes. The 1
Yeah.
and 1 for different prompts, I'm not sure.
You can manage to get 3 of the numbers right, but you cannot
Yeah.
get all 4 numbers like that. That is impossible. And I will show you that in the following. Here, that this is absolutely impossible. So, why is this impossible? This beautiful figure below is the proof. So, VA of 0 denotes what Alice would have answered if we ask her 0, and the other 3 values are similarly defined. So, the number that is marked blue is the probability that both prisoners give the same answer if we say 1 to Alice and 0 to Bob. Because the marked number is 1, they always give the same answer. We can write this as VA of 1 equals VB of 0. Similarly, VB of 0 is equal to VA of 0. And VA of 0 is equal to VB of 1. Now if you combine this, we get that VA of 1 should always be equal to VB of 1. But this red 0 here means that they are never equal. This proves that there's no plan that the prisoners could come up with that produces the table, as long as they aren't able to communicate. If they are able to communicate, our proof falls apart, because then VA isn't just a function of QA, it is a function of QA and QB. And when I say able to communicate, I mean able to communicate after they are separated. So this this is a proof that works, that shows that this probability table is impossible. And it works by asking yourself the question, what would have Alice or Bob answered if we had asked a different question? With a slightly more complex argument, what one can show that this table here is also impossible. I've actually shown in the handout mathematically that this is also impossible. Note that this impossibility is also known as violating Bell's inequality or violating the CHSH inequality. So to summarize, we found that there exist probability tables that are impossible for the prisoners to produce without communicating. In the second section, we learned that you absolutely cannot send information faster than the speed of light. We also learned that if 2 events are far apart in space, they happen close. We also learned that if 2 events are far apart in space but happen close after each other, there exist transformations that swap the order of events without modifying observable behavior. And communication is impossible if you can swap the order of events. The problem now is that there are physical systems that produce these probability tables even when they are far enough apart, which is a problem. Now, which physical systems am I talking about? How can you produce those impossible tables? One possible solution is that each prisoner corresponds to a quantum system with two states. So our Hilbert space is c squared for the first particle times c squared for the second particle. In the beginning, the particles are in this entangled state psi. Saying 0 to Alice corresponds to the A0 operator here. The other three operators are similarly defined. Each of those operators has the eigenvalues +1 and -1. Now if we calculate it, we get the probabilities from the impossible table. I don't actually expect you to read this here, but if you want a QM1 exercise, take the last slide and see if you can reproduce those results. Now, this actually has been experimentally verified. The choice of QA and QB was randomly generated. The distance between Alice and Bob was 1280 meters, which is, if you divide it by the speed of light, larger than the time difference between the random generation and the measurement. So this experiment is free from any loopholes that might allow communication. They had exactly this initial state and these measurement operators that I talked about. You might recognize these operators. They correspond to measuring... Oh, question for the audience. Anyone knows where this operator comes from? Anyone that has ever seen this operator? No one has seen this operator?
Spin, right?
What did you say?
Spin?
Yeah, you're right. Those are the operators that correspond to measuring the spin along an axis that is the z-axis rotated by the angle alpha. So they created our Alice and Bob system as a real experimental system. Alice and Bob were two separate diamonds. Each one has a nitrogen vacancy sensor. That means that one carbon atom was replaced by a nitrogen atom and one adjacent one is missing. The NV center has exactly one unpaired electron. And this electron is a spin 1/2 particle. This spin is the two-state quantum system that we talked about. It is initially prepared in this superposition here. Then the spin up state gets excited by a laser, relaxes it, and emits a photon. That means that the electron spin and the photon number is entangled because the emission happens if the spin state is in a spin up state, and the emission does not happen if the spin is in the spin down state. Therefore, we are in this state here, where the numbers denote the number of photons. Both photons, if they exist, would enter the same beam splitter. The beam splitter is shown in the middle here. So if we measure exactly one photon after the beam splitter, we are in this state here, in this state shown below, because the spin down part falls away, because in that case no photon would have been emitted, and the spin up part falls away, because in that case we would have measured two photons. The phase phi here depends on the pathways of the beam splitter. If it's pi, we get exactly the initial state I talked about. So if we measure exactly one photon, we know that we are in the right initial state and begin the experiment. Both random number generator starts and the spin is measured using microwaves, which polarization depends on the output of the random number generator, and the emitted photons are measured. They managed to prove that they have violated Bell's inequality. They have measured a probability table that is impossible to produce without communication, even if you take all experimental uncertainties into account. Now let us reiterate over what we have just covered. We have two completely separate systems with no physical connection at all, separated by a kilometer of concrete. And still each system seems to know what we do with the other one. And they know it instantaneously, faster than the speed of light. It gets even crazier when you realize that you can do this with nearly any two systems that are easily isolated from the environment to ensure coherence. And all you need to do to entangle those two systems is store the same random value in both systems. We saw that we cannot write the measured value VA as a function of the parts of Alice and the random value, and I cannot overstate how important this is, because we can do that for all classical systems. That means that it is impossible for this means that it's impossible to emulate this quantum system using classical systems like computers, because no classical system can transfer information faster than the speed of light. This means that quantum physics is something truly different than classical physics. Oh, sorry. So you might ask, why doesn't this break special relativity? I said earlier that anything that transfers information faster than the speed of light can be used to construct unsolvable paradoxa. And this is correct. So you might think that our findings from the last section are impossible, or that special relativity must be mistaken. However, nature has found a way to weasel itself out of this paradox. We cannot describe the system independent from each other, and if we would want to simulate it, we would need to transfer information between them. In other words, saying 0 or 1 to one of them would change whatever internal representation our simulation uses to represent the other one. But as I said earlier, the origin of the rule that information cannot be faster than light is that there exist Lorentz transformations that swap the order of those events, but do not change anything observable. And the key point is that whether they say QA to Alex and then say QB to Bob, or whether we say QB to Bob and then say QA to Alex, is irrelevant. In both cases, we get the same results with the same probabilities. The probability table stays the same. This means that quantum physics is still Lorentz invariant, because the Lorentz transformation will swap the order of both events, but the order is irrelevant. It is mind-boggling how in one inertial system Alice was questions after Bob, and Bob affected Alice. That means Bob transferred information to Alice, and in another inertial system it is the other way around. Which is why this experiment deserves the title of the most crazy experiment in physics. The fact that the order is irrelevant also implies that we cannot use this to transfer information ourselves. If you calculate the probabilities of our example, we see that the probability of measuring +1 is always 1/2, independent of what we do with the other particle. To see the proof that the particles did communicate, we need to look at the correlation between both answers, not just the individual answers. And we can only look at the correlation data, what we transferred the answer in some classical slower than light way. So we cannot use this to transfer information faster than the speed of light. The cool thing here is that the entangled states are at the edge of the definition of independent. Depending on how you define independent, they either are independent or are not independent. They're independent enough to not allow us faster than light communication and to not break special relativity, but at the same time not independent enough to allow us to write the answer as a function of the past in some random value. That's it. That's the most crazy experiment. That's the end of my presentation. Do you have any questions?